going little bit fast. So they have complained, written email. I understand. Maybe that is true. Some students have also complained about connectivity issues. Somebody from Odisha writes and considered only the pitch motion, roll and yaw will be neglected. So pitch motion will be there and vertical motions will be considered. The pitch plane model of a vehicle would look somewhat like this. So let me draw the vehicle. So some kind of a vehicle is there. Let's say CG is here. It has some road profile is there. Some horizontal velocity is there. We will assume that to be constant. Then we will study the motion only vertical. This is vertical velocity called heat. And this rotation dot is pitch. Okay. So previously we have considered some kind of model of a quarter car of a vehicle. Quarter car model is used to design suspension. Likewise, this pitch plane model is used to evaluate the passenger comfort. Is for passenger comfort. Including rough road, bumps, braking, and acceleration. So these are four possibilities which give pitch. A rough road will give vertical bounce or heat. When there is unequal bounce on two wheels, we will get pitch. Bumps will give pitch. Likewise, if you suddenly start the vehicle, then because of acceleration, the reaction force, MA, that will produce a pitch where the front of the vehicle will go up. Whereas if you brake, the front of the vehicle will move down. That is, it will try to nosedive. Same thing if you are driving a motorcycle and suddenly brake, your rear wheels might lift up. So these are the four possibilities that can be studied with a pitch plane model. Right now, we are not considering braking and acceleration. Braking and acceleration will change the horizontal velocity. We are considering only rough road and bump. So if this is the car, then we can represent it in equivalent form. Like this. This is our car body. Here is, let's say, CG. vertical velocity is y dot. This velocity is theta dot. Let's say there is a point B, there is a point A. This A and B are suspension fixation points. Okay? So below this, suspension is fixed. So let's put the suspension. Suspension has some stiffness, some damping. Here also, there is suspension, some stiffness, some damping. Let's call this KA, front side stiffness. This is rear side, yes, damping of front side. This is stiffness of rear side. This is damping of rear side. So this is front, this is rear. Slightly moves. What about it? This car body, let's say its mass is M, rotary inertia is J, about its center of mass, M and J. So that is the car body. Then let's say the distance of suspension fixation points are A and B. This A plus B is called wheel base. Wheel base. That is distance between two wheels, because wheels will be more or less aligned below this. Now, where is this suspension connected? Suspension is connected to axles. So we have axle. This is axle. Let this mass be MA. So these two is MA. Now what else is there at axle? There is tire. Tire. This tire, if you take a tire after giving pump and you put it on road, you will see it bounces a lot. It bounces a lot. That means it has very low damping. Tire itself, inflated tire has very low damping. So if the tire is inflated, you can approximate it as a pure stiffness. Of course, this stiffness depends on tire pressure as well as tire temperature. Those of you who follow Formula One will know that the drivers do a lot to maintain the tire temperature, because the tire temperature will ultimately give the pressure. It will adjust the pressure, increase the pressure, and increased pressure means increased tire stiffness. So I will represent this tire as a pure stiffness. This I will call KT. Here, this is KT front. They are different because tire pressures are different in front and rear side. Then what we have? Because of the road profile, when the tire goes over this with certain velocity, let's say we are assuming Vx or V, then we have a vertical velocity, Vy, that is dv dy by dx to V. So we have a vertical velocity. These vertical velocities are different for front and rear. So front will have some velocity, vertical velocity. Rear will have the same velocity after a certain time. The phase between phase,
Sir,
yes,
sir, we are not taking drive from the engine, right?
we are assuming constant speed. Okay. So if we take drive from the engine, then we have to also model the horizontal motion, which is called surge motion. Okay. I will give you one wheel with drive. One example with a, I am not taking the full vehicle with drive. I will take just one example with a drive. All right, one wheel. You
Yes, sir.
can, whatever chapters I have said, at the end of the contract related chapter, you will see there is a drive for electric vehicle. So if you are interested, you can read that part, and I will in future send another chapter which is fully vehicle modeling. All right? Okay.
Yes.
So right now, let us use this simple model. Okay. So phase between EA front and rear is basically wheelbase A plus B and the time taken to do that A plus B by B. That is the time delay. Okay? That is the time delay between front and rear wheels. So whatever front wheel encounters, rear wheel will encounter the same position after this time because we are assuming constant speed and also we are assuming that the vehicle moves in straight line at constant speed. However, if the vehicle takes a turn, then this will not be true. Front and rear wheels will not move through same place. So whatever it is, let's put somewhere here. This particular velocity is V rear as a function of time. This particular velocity is V front as a function of time. Here, MA is axle mass, including all kinds of differentials and other things. Okay, whatever are not part of the car body. So this is called unsprung mass. And the car body mass, including the mass of the passengers and other things, luggage and so on, that is called sprung mass. So MA is fixed, M might bend. Including etc.
Sir, what is MA?
MA is that axle, differential, all those things. See, those things are supported by tire. Okay. And then,
Yes.
yes, so this is basically in a vehicle, in a car, you do not have two suspensions, you have one suspension. Tire itself is a spring which acts as a suspension. Whereas, if you go and look at a train, if you closely look at a train, you will find there are two suspensions. Because train doesn't have tire, train has solid wheels. So over the wheels, something is mounted which is called a buggy frame. So this buggy frame and wheel, in between them, there is a suspension called a primary suspension. And then from buggy frame to the coach or car body where you travel, there is a secondary suspension which is usually some kind of air screw in modern vehicles. Okay, so there are two levels of suspensions in each vehicle. So in railways, these two suspensions are there because you need two suspensions because wheel is not flexible. Whereas in road cars, okay, we have only one suspension, the other suspension is the tire. So we have this. Now to model this, what we need? Distinct velocity points. So what are the distinct velocity points? We change the color. Okay. So we have y dot and theta dot. Those are two velocities. In addition, we have a point here B. Let's say here the velocity is y dot B. At point A, let the velocity be y dot A. These are two different velocities. We do not consider the x velocities due to rotation. Alright? We are only considering vertical motion. You understand with theta dot, point A and point B will also have little bit of x velocity. That depends on height of the CG. So we are not considering the height effect, only the lateral distances are considered. Then this axle, we will put a coordinate system there. Let's call it some y dot C, and this one is some y dot P. Then of course we have down, we might put a coordinates there, may not coordinate. So we have here six coordinates, and ground, including ground, it's 8. So these are 8 points. Out of these, we can write kinematic relation y dot A. It can be written in terms of y dot and theta dot. It is vertical motion, whatever visible is translation, and due to rotation, y dot will be influenced by minus a theta dot. Theta dot is positive anti-clockwise. Okay, so for positive theta dot, point A will move down by a times theta dot, and y dot B is y dot, and that point will move up for positive theta dot, so that is plus b theta dot. These are our kinematic relations. So we only need this. The suspension part, whatever you have taught, I have taught you earlier, you can model. That's not a problem. That's just a spring mass damper system vertically. So suspension part you can model. Only thing that is new here is that car body. So I will try to model this using these kinematic relations. So I will start basically from y dot and theta dot. This is my kinematic relation. Okay. So I will put, as usual, one junction for each independent, each distinct velocity point. This might be independent, might not be independent. One theta dot, one y dot. Let's calculate velocity y dot b. So what do we have to do? Theta dot has to be multiplied with B. So transformer multiply with B. This flow is theta dot. This is flow. So here flow becomes E theta dot. Fine. Here flow is Y dot. We have to add this. We have to add two flows. One junction is same flow. So it cannot be one junction. One junction is same flow. Zero junction is same effort, algebra flows. So this has to be a zero junction where we can add the flows. So I make a zero junction and the result will say 1 y dot t. That is velocity of point B. Your flow is y dot minus a dot, which is same as velocity of point B. So that's how the kinematic structure is.
Excuse me, sir,
Yes, yes,
just a little clarification.
yes.
So this pitch is making this car body tilted, right? But this relation ya is equal to y dot minus a theta dot is only consistent when the car's plane is horizontal. So it has to have some cos sine theta or sine theta term of, I mean, something like that.
No. You are, see,
Small angle approximation.
this is only horizontal motion we are not considering. Okay. We are considering that at this point there is no x dot a. The motions, if you look for this car, okay, motions are small with respect to dimension of the car. Right? So actual thing is you take a cross product from this some distance, rho a, then your cos theta sin theta will come.
Yes, sir, I understood.
Okay. All right. So this is one part of the kinematic relation. Point B's velocity is calculated. Likewise, we will calculate velocity of point A. Transformer, this time it is minus A. And add it with y dot. So this is flow is minus A theta dot. Your flow is y dot. Add them up. You get 1 y dot A. Your flow is y dot A. Okay? So that's the simple kinematic structure. Now on this, whatever inertia are there, we will add. So at theta dot, we have rotary inertia of the body. That is rotary inertia of strong mass. Here we have mass of the body. We also have gravity. So we added all things. That completes the car body part. Now, after car body part is complete, rest of the part is very simple. We can draw that. So what is there? There is y dot c and d dot t. Let's start from rear side. One y dot c And another one is basically same as I didn't introduce another.
Sir,
Yes, yes. Tell.
Why we take this source of effort as minus mg and not plus mg?
Our coordinate system is upward. Positive velocity we have taken upward positive. Okay. If I take
Okay.
downward positive, I will take plus.
Okay, sir.
Whatever you do, it doesn't matter. You should maintain always the right hand coordinate system rule. That theta dot should be taken correctly. All right. Okay. So right-handed coordinate system you choose, whatever you do. So we have a velocity from ground. Now, as we have done for the previous case, we'll do here same thing here. I will connect the mass of the unsprung mass here, the weight of the unsprung mass. Okay. Then between these, we know how to model that. We will take a difference, zero junction. Yes,
Sir, on the right,
yes,
it should be F is equal to y dot plus b theta dot, right? In the
yes,
bond diagram.
yes. By that plus B theta. Oh,
It's written minus it.
that is A side I have written. Yes. Correct. This side is y dot minus A theta. This is y dot plus B theta. Right. So this is y dot A is y dot minus A theta. Okay. So as we have done previously, we will take relative velocity y dot A minus y dot C. So here is y dot A minus y dot C. You can choose whatever. You can choose y dot C minus y dot A, doesn't matter, but should not make it y dot A plus y dot C. All right. So one in, one out, so that you get a relative velocity. If you add them, then it's some arbitrary coordinate system. You will get the results, but it will be difficult to interpret the results. So here we have stiffness, K of rear suspension. This side again. This R of rear suspension. Then between these two, whatever you want to take, doesn't matter. You might take like this. You take relative velocity. And here is stiffness of the rear tire. And of course, here is a source of flow. This is our ground excitation. The rear tip. So this part of model is pretty clear. We have already done it. So this part can be simplified. So this can be simplified. And that simplified model I will put here. Okay. So what simplifications we have? We have here straightforward simplifications. This one junction with two bonds will go. These two will merge. This thing will become 1 y dot A, then 0, then 1 y dot C, then 1 C R. This is what it will become. Okay? So I will simplify it and draw it straight. So once this one junction is gone, this SF will directly connect to 0 junction. So the simplified model will be like this. You have 1 phi dot B, 0, 1, B is to K front, R is to R front, then you have 1 I into mass of axle. This also can be different from front and rear. Source of effort is equal to mass of axle into G. Then you have 0. Here C is to K tire front. Great source of flow is E front. See, this Y dot B is a dummy junction with only 2 bonds. Y dot B is dummy. This can be removed. Same thing will happen to Y dot A. Okay, so left side is created, right side is simplified. Yes, any questions here?
Sir, if we were to consider drive and friction forces on the tire, would we model friction as source of effort or would it be a resistance element?
Resistance. I will do it. Okay. I will just do one tire. First, let me put a passenger on this. Okay. Then I will do the tire. Okay. So this is what it is. We can reduce this further. So I will just draw the final model there. So we have 1 theta dot I is to J D that one junction will be removed, so I am not putting that. Now here, straightforward, that one junction is removed. So C is to J, this is suspension front, R front. How did that come? We removed that one junction. After removing that one junction, these 2 zero junctions, these are 2 adjacent junctions of same type. So we can merge them. So first we remove that one, then two adjacent junctions we merged. So that becomes same one junction, the same zero junction. So I put straight that suspension, this part there, and then another one, and rest of the things remains as it is. How was the power direction? Let me check. We will retain that same thing. One, then you have zero. A tire front, force of flow equal to E front as T. And same thing repeated here. Other side is similar. A is to minus mag, 0, A tire rear, source of flow to E rear T. So that's the reduced model. Inertias are missing here. I will put their inertia. I M and source of effort. T. So that's a very simple structure. Only the car structure is this transformer structure minus AB, that is new. The rest of the part you have learned from your previous class. So I will give you this slide. I will anyway generate this PDF. So you will get. So let me just do something. Let me add a passenger on this car. N number of passengers, okay, 4, 5 people, or maybe one driver. Okay, some people can be there. Let me put one passenger in this car. The passenger itself can be modeled in details. I am not going to detailed modeling of passenger. What I have is this car body. Whatever. In this, let's say I have a seat. In this, I have a passenger. Let's say the seat, you know, seat has some cushioning effect. So the seat part is, let's say this is CG. Seat is, this point is at a distance. Let's say C. All right. So this we will model the seat. Seat itself is a spring damper. Basically, good deal of damping is there. It's a cushion. This is K seat. This is R seat. Then there are various types of models of this human body. Some assume this backbone to be some stiffness for spondylitis and other thing modeling. Some have assumed head and other things. So rest of the model can be there. The rest of the human body model. So here is seat mass. If seat itself is not as a whole moving, okay, not vibrating, seat mass means it's an effective mass of the cushion. So it's the cushion mass, some cushion mass, effective cushion mass. LE. Backbone. And then you have, let's say, head. And here we will have some excitation, some D seat. So basically the model is not difficult. For the same thing, we will find the velocity of this point C. So what we have? Velocity of, or let's say y dot C equal to,
Sir,
yes, yes,
sir,
tell.
what is this KB, this backbone, this KB? Can you explain this KB?
KB is effective C. These models do not actually take backbone as a, they are experimental models. Okay. So these experimental models are fitted into various spring mass damper combinations. It's not simply backbone stiffness. Alright. I have represented it as a backbone stiffness. But actually, there are different parts within that backbone. They model somewhere thorax. There are a lot of degrees of freedom are there. And each of these springs are also not linear, they are non-linear. So they create a model, then they do some experiments, and from experiments they identify those parameters, the values. So those are, okay, some biomechanics problems are there. Okay, we don't worry about that. Whatever will be there, there will be some spring damper things. Alright. So if necessary, I can send you some documents with the models of these also are available. So right now, okay, let us assume the person has, if it has some kind of stiffness, okay, then we can represent it as KB. It's not that simple as KB. There are other masses and other springs in between. Okay. So this KB is nothing like physical quantity. It represents backbone, but it's not really. If you compress the backbone, that's the stiffness. It's not that. So
Okay, sir. Okay.
Okay, so means I have done simplification. This is not the thing, real thing. So y dot C is y dot plus C theta dot, that's it. Alright, okay. So how do we model this? We model like we have done for rest of the things, A and B points. I will create y dot plus C theta dot. So I am creating that there. In my existing model, I am adding y dot plus C theta dot in a different column. Y dot comma C dot y dot. 1 y 3 dot, then rest of model. That we know how to do. Like this, we will develop rest of the model. So, okay, this is how we can extend the model. 1 passenger, 4 passengers, doesn't matter. We will put as many passengers are there. They will be at different distances. We will put them. Because this is a pitch plane model, the sidewise sitting is not considered. Right? So it means we are assuming that okay, the CG location, okay, doesn't means whatever CG location is there sidewise it sits, that is not accounted in this. Right? For that you have to go for full 3-dimensional model. So this is a simpler model. Now in this there are some other things which we can observe. Let's say this zero junction. What does this give? This gives a common force. So this is front suspension force, let's say. This is rear force suspension rear. Yes. So what we have? Front and rear suspension force. If that is there, what is the force at CG? Vertical force at CG? Look at this picture. What is the vertical force at CG? If you look at this, the force acting on the CG is minus FSF minus FSR. You see this one junction? One junction, something, this is connected to inertia. Something. Let's say this is bond 1, 2, this is 3. Flows are equal. What are the forces? E1 is minus, all are minus from junction. Minus E2, minus E3, equal to 0. So E1 is equal to minus E2, minus E3. So what's minus? Suspension force. Here we have taken tension as positive because of our power direction. But usually there will be compression. So compression itself will appear as a negative thing. Tension is taken as positive. So if it is in compression, force will become negative. So negative of negative will be positive. Alright? So the force acting on the mass is sum of FSF plus FSR. So force total Fy on mass equal to minus, because of sign convention, FSF plus FSR. That is from one y dot junction. Okay? So from one y dot junction, we get force on mass is minus FSF plus minus FSR. If you look at one theta dot junction, what is there? You are yes,
Sir,
yes.
what about the gravitational force, sir?
That will be there. That is extra. This is
In the
that is there. Minus mg will come. That will come also. Okay. I have taken 3 bonds here. Okay. 4th bond is there. That will come. Okay. That will come as minus mg to this mass. Okay. So I wrote for this mass where I had 3 bonds. You have a 4th bond. So you will add this minus mg. All right.
Sir, that is present in the previous bond diagram, right? On the junction 1 y dot.
Yes, it is there in previous
Yeah.
one. We carried it from there.
Hmm.
Yes, it is there. Okay. We carried it on from there. Everywhere mass is there, we have considered minus mg. If you want to analyze the system from equilibrium position, you can say I drop minus mg, but then if you drop minus mg, you will not be able to model discontact from the ground. Contact and discontact from the ground. For example, in true modeling, if this spring KTF, this spring you see, this KTF, if it comes under tension, suppose its state, that is displacement becomes tension, then this stiffness becomes 0. Because road cannot pull the tire. Alright? Road can only under compression, that tire will give force. Tire cannot be under tension. So basically it is a switched stiffness, which we are not considering. So if you have to consider that kind of a bouncing car can discontact from the ground, let's say going over a bump, it bounces at such a speed that it basically flies up from the ground. Then we have to make these nonlinear springs. Nonlinear springs, and if you do not have minus mg, that car will not come down. Okay. So if you want to analyze from the static equilibrium and drop this mg part, then that will be valid only for the case when the car doesn't bounce from the ground. So where was I? Okay. This one theta dot. So one side we have here some force, here some force. So what is the force there? If this is FSR, here force is FSR, your flow was theta dot, this became minus a theta dot. Forces scale opposite. So this becomes minus a times FSR. And this becomes E times FSF. That is the force. So those are basically torques. Torques due to the suspension forces, those will be added and they will act on theta dot. So you have moment about z axis. So at one theta dot, J, we will have mz on J. We turn out to be minus of minus becomes plus. Okay. So I will write A times Fs here minus E times Fs front. These itself are negative. Fs and FSF, those will be negative. So what did we get? We wrote our equations or only kinematic equations. We created our model based on kinematic relations. But you have got force balance and torque balance correctly. You didn't write those equations. Those have come automatically. Why has that come? Why we modeled with kinematics, but why dynamics has become correct? That is because of this power conserving property. So what has happened? Power conserving property that means no storage, creation or loss. Of constraints that is 1, 0, transformer and gyrator. These are the constraints. Because of that, a model created from kinematic analysis gives correct force and moment equations. That is for mechanical domain. Similar things happen in other domains. So this is what happens, and I will also add here and vice versa. That means if you create a model based on force and moment equations, you will see kinematic analysis becomes correct. So one of the thing you make correct, either kinematics you make correct, force and moment balance will be then correct, or you do correct force and moment balance, then kinematics will be correct. So you just need to concentrate on one aspect of the model, the other aspect will be automatically correct. So because you have asked, I will now move on to wheel. Okay, so in this
Sir,
model, yes,
can you
yes,
give
yes.
an example where this power conserving properties does not hold?
Power conserving properties do not hold. See, all constraints are always power conserving. Power conserving properties, whatever loss will happen, that will happen through some kind of dissipation or source. That's it. Okay. A inertia, a compliance, they cannot dissipate energy. We are talking about
But
only
the
junction
viscous
factor.
temper,
That will dissipate. That will dissipate. See, that is not junction part. That is not constraint. Constraint is this 1, 0, all this. Alright? The constraints, relations are modeled by constraints. Those are external things. This C, R, I, these sources, gravity, or whatever, those are external things. They are not part of the constraint. What we are saying is constraint is power consumption. Constraint cannot say you have electrical conduction. So your particular resistance or particular capacitance or inductance, they may have some loss. But when you are joining them at the connection point, if you have connected them correctly without resistance, okay, without some resistance, okay, let's say if you have loose connection, you have connected them correctly. How do you say at that point there is loss of power? Okay, it's about constant means. Basically, in electrical circuit, it is a point. It is a point at which you have made parallel or series connection. Likewise, here constant means it's how the things are connected together. That's the equation. Okay.
understood, sir. Now it's clear.
Okay. Other external things will dissipate energy. I will give this example of, let's say, wheel. Okay. So in this, I have considered only FSF and FSR. Additionally, the force will come from this person. This whatever the person driver is sitting there, the driver will create a force there on y dot. Alright? Driver's inertia, driver's weight. We have to put there everything in the model. So those will also apply some force on y dot. Those will also create a moment at theta dot. So that will also come automatically. So let us now model a rolling wheel. how this wheel will be coupled to the vehicle, you see whatever chapter I have sent there. Right now I am modeling this wheel as a completely separately. Alright? So let's take a wheel. Let the wheel have some horizontal velocity v, not constant. It has some rotation, let's say omega. Some torque is applied on this from engine. T. If you have some kind of engine or some kind of motor, you can model them. Right now, I am assuming some external torque is applied on. And what else? On this, there is normal reaction. Put it in this way. There is friction. That's it. So this is for case. And let's say take the radius as R. Actually, this radius will be radius at the contact pad, not the radius of the wheel. This will have some deformation. So radius at the contact pad. So in this, we will put a coordinate. This is theta dot, not constant. This is x dot. This wheel has mass m, total inertia j. So how do we create the model? First we create slip. What is slip? Omega r minus the horizontal velocity, or r theta dot minus x dot. That is slip. Now what is friction force? It's mu times n. Now what is this mu?
Static.
No, it's not. The tire is
Anyway.
not.
Or rolling friction, okay? Probably.
Not even rolling friction. Rolling friction is useful when you are talking of big wheels on some surface where static friction is very low, such as in ice or things like that. So if you see any problem on rolling friction, you will see it is there somewhere on a glass or on ice, big wheels like that. Okay. In normal vehicles, unless the wheel is flat, suppose somehow or other it has got punctured, then you will not have significant rolling friction. Rolling friction comes because if your tire has become flat, let's say, tire has become flat, then you will have rolling friction. Okay?
Yes.
Okay. Or the ground is muddy. Okay, ground has deferred. Okay, soft ground. Okay. So in those cases, you will have rolling friction. Otherwise, this rolling friction is nothing. Actual important thing is aerodynamic drag on the vehicle. That is what is the major loss factor. Okay, so this mu, okay, we have time, so I will draw this mu. This is the ratio. This ratio is basically the slip I will write, let's say sigma. So this is not slip, this is slip. Okay, sigma x is given as r theta dot minus h dot divided by r theta dot. This is during acceleration.
Okay, sir. So when there will be slip, it will be kinetic friction.
Not even kinetic friction. Okay, this big changes. Okay, like this. Meanwhile, so this has picture has gone wrong. Okay. something like this. I will draw another picture. So this is how this mu changes. Right. This mu, this value is, let's say, around 0.8. This is for asphalt, dry asphalt. With our normal road. Okay. This is, let's say, for wet asphalt. This is for ice. And so on. So this is how mu changes. And this value of mu is maximum here. This value you see, this value is maximum between 0. I have forgotten, around 0.05, 02 to 0.05 or something like that. Okay. So this is where actually we do friction control or anti-lock braking control. We always try to maintain. Okay. Suppose you break the wheel suddenly. What will happen? If you break, let's say omega is equal to 0. E is not equal to 0. Okay, braking. Under braking, the sigma x is defined as x dot minus r theta dot by x dot. This relation is not valid because r theta dot becomes 0. Okay, can become 0. So under braking, this relation is applied. Okay, and this will become negative. This is less than 0. This slip is negative. So this is magnitude of slip ratio. Okay. So if somehow or other omega is equal to 0, then sigma is equal to how much? 1. So sigma is equal to 1. Maximum value is 1. This is 1. So what you get at 1? You get lowest friction. So if the wheel starts slipping, wheel slips means wheel is not rotating, it is skidding on the ground. Once it starts skidding, your friction will become low and you will not stop. It will take long time to stop. So the friction is function of the slip ratio. It's not constant. Once the vehicle starts skidding, if you are driving some kind of motorcycle or scooter or something, you might have experienced. Okay, that if you suddenly brake, suddenly apply brake, then it will skid. So what does this ABS do? Or if you are driving a motorcycle, what does it do? You don't brake suddenly. You brake, release, brake, release, brake, release at a quick succession. So that you do not reach very high slip ratio. So what you do? You reduce your omega. Okay. And as omega reduces too much, slip increases, you immediately release, then again apply brake, release, quick succession. That is what ABS does. Alright? Okay. So ABS maintains maximum friction at this 0.02 to 0.05 by successive braking and successive releasing. Okay? There is some kind of falsehood modulation there. Okay, we will not go into details of that. What we have is a very simple model. So this friction is a nonlinear function. Normal reaction incidentally is constant here. If you have suspension dynamics and vehicle dynamics over that, then you will get normal reaction from there. This suspension force, FSF, this tire force from this C, whatever you will get, that zero junction will give you the normal reaction at front tire. This zero junction will give you normal reaction at the rear tire. So this normal reaction for a full vehicle model depends on suspension dynamics and it's not constant. For this wheel, we are assuming normal reaction is constant. For this mu changes, mu is a function, complex function of x dot and theta dot. So how do we model this? So I create first two one junctions, one theta dot. Here I put the inertia of the wheel. Then I put the linear velocity. That dot 1 y dot. Sorry, not y dot. We are not modeling y dot, normal reaction. We are modeling x dot. One x dot. Here we have mass of the wheel. Then we calculate slip. So the slip we transform by r. Then we take minus this is r theta dot. This is x dot. So r theta dot in, x dot out. So how do we do this kinematics at a zero junction? So what is here? Here it is. So is r theta dot minus x dot. It can be positive, it can be negative. During acceleration, slip will be positive. During deceleration, slip will be negative. And here we put a resistance, which is resistance due to friction, which is a nonlinear function. Nonlinear function of x dot and theta dot. Let me write x dot theta. So that's a nonlinear function. What else we have? We have a dot applied. If t greater than 0 for acceleration, t less than 0 for braking. Okay, so when you apply brake, you apply an opposite torque. Now what we get from this resistance generates the friction force. So this is F. I will change that nomenclature to something else. That I will not write friction force. Let's call it capital F. So that it's different from Von Graf flow. So this is friction force. So we will get here effort equal to friction force. So what will be effort here? If that is the friction force, efforts are same. So this will be same effect. This will be same effect. Here flow is theta dot. Here what will be the force? R times F. That is the torque, reaction torque. So what you have? What is going to J? Here effort is T applied minus R times the friction force. Okay, here it is the friction force and x dot. So what is driving the thing? Driving force is friction force, and driving moment is the reaction moment is this friction force, whatever friction force, sorry, Fa. If you transfer it here, okay, equivalent force system here is Fa and Rff. These are the equivalent force system. of friction force. So friction force propels the vehicle forward. It is traction. Friction force, that is traction force. Or traction force. So traction force moves the wheel forward. Traction force opposes is the power direction. Traction force is in having positive power direction towards x dot, and it creates a negative moment at theta dot. It opposes rotation of the wheel, whereas it moves the vehicle forward, wheel forward. If this traction force becomes negative because of negative slip due to braking, somehow or other this traction force becomes negative, then the equivalent force system signs will change. That means if it is negative, it will try to rotate the wheel. It will try to rotate the wheel forward. It will try to rotate the wheel forward and move the vehicle backward. So it will give a backward force to the vehicle and a forward torque to the wheel. That's how the friction acts on a wheel. Okay. So that is what is for today. If you have any confusion, you can ask.
Sir, in the figure mu versus slip ratio, it is suggested that at zero slip ratio, the mu will be zero.
Mu is zero. Okay. Mu is
Sir,
zero.
but
It's
shouldn't it be equal to?
not our Coulomb friction or this. Okay. Those theories do not, those are idealized things. You see, this is 0.02. Okay. And this is 1. So this is obviously not to the scale. Okay. So 0.02 will be very close to 0. This is very steep. But at zero slip ratio, the friction is 0. You do one thing, you search in the net. That is, you know some tire company called Michelin. It's pronounced Michelin. So in that,
Yes, sir.
in that you search in Michelin document the paradox of friction. Unless you have slip, you cannot move forward. Okay, to generate friction, you must have slip. Like even in our normal static friction case, okay, whenever you are applying a force, we are getting friction force. Right? How is that friction force coming? There are asperities at the contact surface, is it not? Right? How is that friction coming? Right? Two smooth surfaces do not give friction. Let's say this is one surface, there is another surface, which are these asperities interlocking. Okay. So when you apply force, these asperities, these are, let's say, asperities, these asperities bend. Some asperities bend, some asperities break. So because of this, you have a micromotion. This micromotion generates the friction force. Alright? Okay. So unless you have this micromotion, you will not get friction force. Likewise, in a wheel, unless you have micro slip, you will not have friction force. Every vehicle, you see every vehicle when it starts, there is a slip. Every train, or train wheel or even bus wheel, if you look very closely, you will see initially there is a slip. Without slip, that vehicle will never go forward. Okay.
Sir,
Sir,
Yes.
but it can happen that the tire is not slipping and the clutch plates are slipping, and that is creating the torque.
See, clutch plate is another thing. Clutch plate is another thing. Clutch plate has got nothing to do. Clutch plate slipping will create a torque. Okay. How will it create a torque? It will create a load torque on the how the thing is transmitted. How the thing is transmitted. Without clutch plate, suppose you have a clutch plate. What is clutch plate? You have here engine leg. Engine. Okay? You have a zero junction. This side is, let's say, axle and wheel. Or whatever drivetrain. Then between these two, you have a resistance. Alright? So what is this? This is theta dot engine. This is theta dot output shaft. Okay, let's say wheel. It's not wheel. Okay. So what do you get here? Delta theta dot. So this cross plate whatever happens, the torque transmitted is same. This torque will be same. Torque transmitted will be same. The amount of slip will decide the value of torque. This is again a nonlinear function. You have dry clause formulation, you have clause formulations with assumption of uniform pressure, uniform wear, and so on, whatsoever. Some nonlinear relation. This will give you the torque. Depending on torque is a function of some function of this delta theta dot and other parameters, friction parameters and other things. Okay. There it is static friction, kinematic friction, all those things are there. It is usually kinematic friction when it is slipping. That has got nothing to do with this. This resultant torque T will come here. This T will come here. Okay. This is the final T which is applied on the wheel. Alright. Right. If the
Okay,
other
sir.
thing-
So
yes. Tell.
So, both the plate and the tire both will slip while starting the car.
Yes, both will slip. Unless
Got it.
this sleeps, you will not be able to generate this T. That T will not come. Okay.
Yes, sir.
Cloth has to sleep to transmit power to the axle. Axle, then wheel has to sleep to generate the friction force. All of them have to sleep to transmit the power. Okay. Yes, any other questions?
Sir, then what about during pure rolling?
Pure rolling, it never happens in vehicles. Okay. It never happens in vehicles because you have air drag. Okay. So if you have air drag, you have to always spend some power. Okay. Pure rolling never happens. Okay. It's only physics theory. Okay. Our nothing like pure rolling is there. Okay. If you have pure rolling, that's not a problem. Okay. If you have pure rolling, what happens? Hey, this friction force is not defined.
Slip ratio.
No, this friction force is not defined. You will have straight pure rolling H dot is equal to R theta dot. That's it. Okay. You
Yes.
will connect one theta dot and one H dot by a transport R. But that is a theoretical thing. That never happens. That is equivalent to this resistance becoming infinite. Right. This friction coefficient becoming infinite, it will have pure rolling. Okay, any other question?
Sir, but even at this 0.02 slip ratio, like it will seem to be like pure rolling only, right? Because it's so small.
It seems to
Kind
be
of.
Yes, kind of. It's, from outside, it seems, but these are very important because based on this, tires are designed. Tires have treads. If you see this tread design is very, very complex. And then there are radial and other configurations inside wear meshing and so on. Okay. So tire is not a easy science. Tire is very, very difficult thing. Okay. So these are experimental thoughts. Okay. You can find them. There are different formulas. One by
Sir, and racing cars have no tread, right?
Racing cars do not have. They don't have. They don't have. Formula One cars do not have tread. They are solid rubber. Okay, usually solid rubber. But they have puncture of other kind. Okay, inside that is thick, very thick tires. Okay, their tire burst is separate. Okay, any further questions?
Okay, sir.
Okay.
Sir, I think in the definition for slip ratio, I've written R theta dot minus X dot by R theta dot, like in the above page.
Yes.
That is X dot, right? For slip. Sigma X equal to.
Yes. R theta dot rotational velocity means the velocity of the contact point minus the linear velocity divided by the
Linear velocity.
no. r theta dot minus h dot by r theta dot, that can be your right in your mute. R theta dot minus h dot by r theta dot during acceleration. Okay, so that x dot can be 0, but theta dot cannot be 0. Okay, so at starting x dot is 0, this is not singular. Whereas during braking, it is x dot minus r theta dot by x dot. In this case, theta dot can be 0. So you have to avoid singularity. Whatever
Okay,
happens,
the definition changes, like the formula changes during acceleration and braking.
yes, formula changes. Okay, formula changes.
So basically, it's like when r theta dot is greater than x dot or r theta dot is less than x dot.
Yes.
The
That's
formula will change.
formula.
And sir, like, why don't racing cars have tread? Like, tread affects what, basically speaking?
Oh, tread affects side slip. Okay,
Side slip.
so it has handling problems. Handling problems means these Formula One cars are very, very typical. Their tire also deforms due to aerodynamics. You see, like if you know journal bearings, what happens? The bearing is supported because the fluid is flowing through an annular wedge. The space, originally there is more space, then as you go closer to the contact point, the space reduces and then there is pressure generated. Likewise, when this wheel, Formula One wheel, that is wide wheels, they are wide wheels, they are moving forward, near about the contact point, the air is getting compressed there. Alright? You have a wedge effect. So what happens is, okay, in normal vehicles, you have contact point just means rolling contact point is ahead of the vertical point. Okay, if you draw wherever we draw normal, ahead of that rolling resistance comes. But in this Formula One cars, that point shifts backward because of air pressure, because of external air pressure. So this above certain speed, actually, in order to take a turn, you have to turn the steering in the opposite direction. Okay. Normally, wherever we want to take a turn, we turn it same direction because our vehicle's contact point is ahead of the normal reaction point. But there it can go behind the normal reaction point. So they have to do that. And number two is plates are there because we operate in muddy roads. We don't get, if you look where are the largest plates, largest plates are there in tractor wheels or big earth moving equipment where you have mud and other things. Okay, very soft ground. Okay, so our vehicles, we can travel in a country road. Okay, we have to adapt. There, if we have this Formula One type, car type tire, it will not work. It will not be able to grip because there is mud. But Formula One tires are also running on very dedicated track. They don't need that tread. All right. Okay.
Yes, sir. And wet conditions, like there will be slight amount of tread.
Very, very important. Okay, it can aquaplane because of these treads.
Yes.
Okay, so if there are no further questions, then good night to all of you. I will send this, upload this document in